Well, thanks, Tuomas, for being here today. It's great to see you.
My pleasure to be here again.
It's great to have you come and share your thoughts with us at the Microsoft Research AI Distinguished Lecture Series. We've known each other for a very long time. I remember, I think, when you were a grad student, asking all these questions in forums at the international meeting of Operations Research and Management Science. And I turned around and I said, "Who's this really smart guy asking me all these questions?" And I first met Tuomas that way. And what I really was excited about was it seemed we shared interests in operations research, decision analysis, AI, the arc of concepts through all those fields, which only more recently have come together with the current viewpoint on and perspective on machine intelligence. And so that was fabulous. How did you get going in this whole area? 'Cause I knew you had a history in Nokia, being in Finland and working as a young student in areas around probability and statistics. How did you get into this field?
Yeah, I actually started studying management science and industrial engineering, and then operations research and systems analysis and AI really just drew me in as an undergrad, really. And then for a master's thesis, I built the Draconet, which is the first distributed system for negotiation among self-interested agents. And that really spawned more questions than answers, so I decided to come to the US to do my PhD in that. And it's always been kind of interdisciplinary between computer science and AI in particular, and operations research, and economics, in particular game theory.
Yeah, so go back to that project again. What was it called again?
Draconet, or Transportation Cooperation Net.
And what was it all about?
It was this thing where I got to really shape it myself as a master's thesis student. They had sold this project.
This is in Finland?
In Finland, at the Technical Research Center of Finland. And they had sold this project before I joined to some companies that had some trucking needs. Some of them were transporting heavy goods like construction things, and others were transporting very light things and so on. And then they realized that they had some potential for cooperation, reallocating tasks among themselves and so on. And from there, I could just take it in any direction I wanted, and I wanted to build an automated negotiation system.
But how did you yourself get pulled into this?
Well, I had like 3 different options to look at master's thesis, and I liked that as the most open-ended and novel.
Were these practical projects you had to engage in Finland?
Yeah. There was a master's thesis or master's research thesis, and and there were many different options, and I liked 3 of them, and this I liked the best.
And so what got you excited about the self-interested distributed aspects of things?
Well, I had been studying game theory and optimization, and I felt that a lot of the stuff hadn't been put together. So there's a lot of good work on integer programming and things like that, and a lot of good work on game theory. But people hadn't really put those 2 things together.
And did this trucking system work out?
Yeah. So it was just a prototype system. So we collected real data and showed how it would work on real data, but it wasn't ever, we didn't actually field it or anything. That wasn't even the goal. It was really just a prototype. And then I left to the US to do my PhD.
Okay, now before we get into the PhD work and beyond, let's take a brief break and talk about your windsurfing career.
Uh-oh.
So how did that get going, and how did you become the Finland champ in windsurfing?
Yeah, so I've been racing sailboats since I was a little kid, and then you can really sail optimist dinghies until you're 15, but I got too big and heavy, so the boat wouldn't just go. And so I needed a different class, and windsurfing had just become so hot and athletic, and it could actually take a little bit of a bigger guy. So I started windsurfing, and then in a couple of years, some of the coaches in Finland kind of saw me and how I did in the races, and they picked me onto the national team for 4.5 years. So throughout high school and throughout the Air Force, I was actually sailing around in the World Championships and so on in windsurfing, and in the winters we would go down south to practice when Finland was all covered with ice.
Down south where?
Canary Islands, sometimes in Spain.
Where does a Finnish person go to practice windsurfing in the summer?
Yeah.
It's interesting. Yeah, I always was impressed. Like you mentioned this in the past, and I even see in your formal CV,
Yes.
1986. I think it says, Finland windsurfing champ. That was the year.
Yes, and my best race was actually being the 5th in the Europeans. I was also 12th in the worlds, but really the best races were in the Europeans.
Before we get off that, do you still do windsurfing?
Yeah.
Even though it's not hot anymore?
No, it's actually really nice that it's not hot anymore. You have a lot more space to do it.
I thought you'd be on paddle boards by this time.
No.
It's still the same thing. So,
I'm kind of loyal to what I do.
yeah, and never ice hockey.
I played ice hockey as a kid.
Okay, just
Being a Finnish kid, you
yeah,
don't have to.
Just checking in on this.
Yes, I know you play.
So then you went off to Amherst,
Yeah.
and how was that experience, and what kind of things did you work on there?
Great, yeah. I had read a lot of papers in multi-agent systems already doing this transportation cooperation net system in Finland, and I looked at who's publishing most in multi-agent systems and sent Victor Lesser email, and he accepted me as a grad student. We actually flew there to meet before we committed, so we kind of interviewed each other a little bit, and then we decided to work together, and it was great.
I always found Victor, I knew for many years, as a very, very kind, thoughtful, caring man.
That's right. We still talk about stuff, and he's still my mentor.
That's fabulous, and I'm sure he probably some of his personality, his mentorship abilities have rubbed off on you over the years.
Yeah, I try.
And so you finished that up, and then what was next for you, your PhD?
Yeah, so then I went to be an assistant professor at Washington University, St. Louis, where I started my own research group, and then 4 years later, CMU hired me out of there.
And so at CMU, you've been this force in combinatorial auctions and some interesting results you've proved in, and you and your students have proved in that space over the years. And you've not only done this great scholarship, you've been spinning out companies like CombineNet. I think you were running CombineNet for many years. It must have been at least a decade.
Yes.
So what was that all about, the CombineNet
Yeah, so
experience?
CombineNet, I built this, started building the technology in '97. And then I founded the company in 2000. And you're right, I mean, we were continuing until 2010 before it was acquired. And we fielded 800 of the world's still largest scale combinatorial auctions ever fielded, totaling $60 billion. And we created a supply chain efficiency of over $6 billion. So
And of course, they gave you most of that money, right?
Sourcing software is the worst business, I can tell you that, in terms of raw margins.
Well, they give you hopefully a little piece of it at some point.
Yeah, you have to basically sell software to the toughest negotiators in the world. That's what they do all day long. They push the suppliers down on pricing, so they do the same to the software vendors.
And so, what was your experience like with the whole startup world?
Yeah, it was very interesting. You know, a lot of people think that the interaction between academia and startups is like you just license technology from academia and it's a one way. But this was really both ways, actually more so the other way, where we actually saw problems in the real world that hadn't been looked at in academia. And many of those things we actually brought back to my academic lab, and then we were the first ones to look at these things, like preference elicitation in multi-agent systems, automated mechanism design, structured domain-specific bidding languages for combinatorial auctions, etc., etc.
So where did you, when did you start getting involved in going from that realm? And I see the relationships, but some people in the outside world might not see them, to the realm of kidney exchanges. And how did you get exposed to that? Maybe you can explain to folks some of the things that, with the big grand challenge of kidney exchanges is, and why it's a hard problem, and why it's so valuable to solve, and then how you got interested in that. I realize it's a multi-part question here.
Okay, great. So how I got interested in kidney exchange.
What is it, first of all, what is this? Because people might not have any understanding at all about this.
Okay, so kidney exchange is there to help alleviate the problem that there aren't enough organ donors who donate organs when they die. So there's this big imbalance of supply and demand, and not just in the US, but in most countries. Mm-hmm. So for example, in the US, there are over 100,000 people that are listed to wait for dead people's kidneys. And these are people who are very sick and are eventually going to die if they don't get them. So you can do live donation, because most people have two kidneys. Like, if you get sick, I can give you one of my kidneys, or offer to give you one. But chances are I can't, due to blood type and tissue type incompatibility and a few other factors. So that's where kidney exchange comes in. Mm-hmm. So you actually, at the simplest, you swap the donors. So if we're a willing pair, donor-patient pair. Some other pair is willing, but also incompatible.
It can be anywhere in the world,
It could,
essentially.
well, currently they're just within countries, but many countries have them. But so think about in the US, California and Massachusetts, say. So I'm going to donate to somebody else, and their donor is going to donate to you. Now both of the patients can live. If you think about that from a graft perspective, that's a 2-cycle. You can also do 3 cycles, and you can do what we call never-ending altruist donor-initiated chains. So somebody actually gives a kidney, doesn't expect anything in return. Instead of a cycle, that triggers a chain in the network. And at the end of the chain, there's a last willing donor, which can serve as this altruist in the next week's optimization batch. And it's a gift that keeps giving. But the hard optimization problem in the batch setting is figuring out the optimal combination of cycles and chains.
Okay, so that's the challenge. How on earth did you first get exposed to this and get excited about it?
So I was on the organization committee of the International Congress of the Game Theory Society in 2004. And as one of our invited speakers, we invited Al Roth, who had just started working with some medical collaborators and some other economists on the New England paired kidney exchange. And he spoke about kidney exchange, so that's how I first heard about it. And I saw that there were a lot of kind of computer science, the OR's problems in there, and I thought that, hey, that would be a nice way to do some pro bono work. And
to give back to it.
And to give back, yeah, exactly. So this is not a startup. We run the nationwide kidney exchange for UNOS, so we donate the software from my CMU lab.
What does UNOS stand
for?
for?
UNOS, good. UNOS is the United Network for Organ Sharing. They control the transplantation in the US, and both on the deceased donor side and kidney exchange side, at least for the national kidney exchange. And our software runs the kidney exchange side of it. So every week it makes a transplant plan for 69% of the transplant centers in the US. And this is all, we are giving away the software, it's not a startup.
And do you, well, first of all, before I even get into how it works and how you monitor it and so on, what hardcore problems, even if they're just applications and transfer of existing ideas, did you have to sort of work with to solve the kidney exchange challenge?
So one was just this optimization problem, the batch optimization problem. But then as we got more into it, we realized that that's not the only thing. There are a lot of things that go around it. So for example, the problem is dynamic. Patients die, they get deceased donor organs, other kidney exchanges may snipe them, other things might happen, they get sick, they can't be transplanted. So the problem is dynamic. And also new pairs come to the exchange, new altruists come to the exchange, and so on. Another issue is that there are what I call pre-transplant failures. So the medical knowledge is incomplete. If it says that we're compatible, in reality we may or may not be. And turns out that most kidney exchange structures, cycles or chains, worldwide, actually fail before transplant. Because if even one of those edges turns out to be actually not compatible, or one of the patients dies or gets a deceased donor organ, something happens between the planning stage and the operation, which is about 8 weeks typically, the whole structure fails. 90% of the structures fail. So how can we actually do this failure-aware planning? We just had a paper out in Management Science on that, and you can get much better numbers of transplants by not just looking at how good an edge would be, how good it would be, but how likely it is to succeed as well. So now you're taking extra information into account and you're making these more robust plans.
Where does the likelihood come from?
The likelihood
of succeeding, I mean.
The likelihood of succeeding could come from machine learning models, but even if you just say that it's the same average probability across everybody, you get still 100 to 150% lift in transplants. So even if you don't take into account the fact that some edges are more likely to fail than others. And what this looks like then in practice, you have shorter cycles, you have shorter chains, and more parallelism in the plans. So then those structures are less likely to fail because they have fewer edges, and if they do fail, it affects fewer transplants.
I see. And is it the case that a patient and nephrologist and team and family will ever have to do this idea of a trade, like, my kidney function is crashing at this rate, or I can't do more dialysis. It's hard to wait longer, but this match is not great. To wait for the next match and have a probability distribution over the of getting a better match within time horizon T.
Yeah, some people have looked at that as a decision as to how long should you wait. We haven't really studied that so much, and it's my understanding that patients really aren't presented a menu of kidneys or anything like that. It's more like when a matching kidney is found, people are very happy with it. Now, I'll tell you a little bit of a counterexample to what I just said. We were working with the Alliance for Pair Donation. This was in 2006, 2007. It's a private kidney exchange, and there was this I want to say 60-year-old uncle and a 13-year-old kid. This 13-year-old girl, and it was clear that 60-year-old kidney would not last adequately long in that little kid, because the little kid still had a lot of life ahead of her.
Just think, you look at the actual amount of tread you have on the organ you receive into a patient. And this tread is there for the future.
So they were actually compatible already without the kidney exchange, but they came to the kidney exchange and said that you have 3 months. If you can find a better match for the girl, the uncle is going to give to somebody else. And we actually algorithmically found a better match just in the normal process. So now we took this compatible pair, put them into the kidney exchange, and for somebody who was older, that uncle's kidney was great.
Yeah.
And then the girl got a younger kidney.
I hadn't really thought about in organ transplants that you have the age of the tissue itself, and has to be
Yes.
sort of, will these cells live as long as this patient perform over
Yes.
this time when they have their own lifespan as part of the donor's life history. Very
Yes.
interesting. So moving on from the medical successes into other areas, so your team is renowned for beating the best players at Heads Up, No Limit, Texas Hold'em poker. And this is remarkable in some ways in that it goes beyond what we often refer to as the simplicity, frankly, of games of perfect information. You can explain the difference, going from checkers or Go into the realm of uncertainty, bluffing,
Yeah.
the human dimension.
Yeah. So in perfect information games, like let's say tic-tac-toe, checkers, chess, Go, you know exactly what the state of the world is when it's your turn to move. And then you can use techniques like minimax search, alpha beta pruning, and endgame databases, that type of stuff.
And you can build huge databases by just playing oneself a trillion times
Yes,
as well.
yes, and there have been great successes. Some of those games are very difficult as well. Like chess is still unsolved, Go is still unsolved, but they have reached superhuman level at that, and it's very impressive. In imperfect information games, the situation is totally different. None of those algorithms apply. In imperfect information games, you don't know the state of the world when it's your turn to act. And to complicate things, your opponents may know things that you don't know, and vice versa. So you have to think about, what do my actions signal to the opponent about my private information? And I have to think about, what do my opponent's actions signal to me about their private information? And it's this balancing act.
And the history of the evidential stream as well.
Exactly. Well, absolutely. Yeah, you have to think about the history of the actions, because that's where the beliefs get updated from.
Yeah.
So you could think about it as a generalization of POMDPs, but into the game setting. Yeah, so it's much more difficult because you have to think about those beliefs, and then you need to go to game theoretic reasoning. So it's actually interesting that how you should update the beliefs falls out of the classic game theoretic solution concepts like Nash equilibrium and its refinements. But the work is really about, how do you marry those solution concepts with algorithms from AI, so we can actually compute good approximations of Nash equilibrium and its refinements.
Okay, so people have been trying to solve this problem for decades.
Yeah.
What was the magic or the unique innovations that your team came up with it. I have to say, it wasn't in one cycle. You've been doing this for a while now.
That's right.
And you finally got the win. But what's some of the findings and results?
Okay, so there have been a lot. So I've been working on poker as one of the benchmarks since 2004. So from 2004 to 2017, 13 years. So it wasn't like one night we came up with something and it was done. It was just like accumulation of ideas.
I can just see this is the same time span. We have Tuomas thinking about kidney exchanges, and then take a break. Poker. Back to kidney exchanges again.
Yeah,
So-
but that's maybe that's kind of my style of research at combinatorial auctions, where you're 10, 15 years. Kidney exchange was 10, 15 years and still is, and combinatorial auctions too. But it takes a while to really learn the problem and learn the techniques that work. So it's not like one paper and that's brilliant and solves the whole thing. It doesn't work like that. So one is abstraction techniques. How do you automatically abstract the game into a smaller game so that when you solve the smaller game, perhaps even only approximately, the results are good answers, the strategies are good strategies for the original game. The second is the equilibrium finding algorithms. So how do you actually take a game and find exact or near optimal strategies for that game in a computationally efficient way, both for memory and for speed. And there I would say the number one thing that actually got us over the finish line at the very end, clearly there was accumulation of work up to then, but the last thing was these sub-game solving techniques, safe new sub-game solving techniques that really got the final jump, 63 millibig blinds per game jump.
We'll say more about that. What goes on in the subgame plan?
Yeah, so normally if you
What do you mean by subgame plan?
Yeah,
Also?
so if you normally think about perfect information games, you can think about, let's say, talk about chess. So you get to a state, and then you start thinking about what do you do from there. You think from there to the end of the game or to some virtual end of the game, if you will. This is easy, relatively speaking, in perfect information games, because you can solve the game theoretic solution for a subgame based on information only in that subgame. In imperfect information games, you can't, because you have to think about the balance of strategies across multiple imperfect information game subgames so as to not give out too much information for your opponent. And what these subgame solving techniques do is that they take this idea of subgame solving into imperfect information games, which is very different than in perfect information games. And the techniques actually look totally different. But still we can find provably optimal subgame solving techniques, so we don't have to look at the whole game at once. And therefore, in the subgames, we can actually solve much finer grained abstractions, come up with much better strategies than you can afford to computationally do if you try to solve the whole game monolithically.
Let me ask you something. If you see how hard it was to solve some of these problems and to get to the level of that could beat a human or a set of top-notch humans in this space, how on earth do humans do such a good job at this?
That is so amazing. That's a great question. So these humans, they just are, I can't even describe it. They're just so good at this game, which is so hard. And they can talk about these detailed things. Some of them don't even have college degrees. Many of them actually do, and some of them computer science and economics and so on.
Probably inversely correlated with their skill set.
But they can talk about these concepts that they've really learned in this game-specific way, which is very interesting. And they also have amazing memories about the game. So one guy was one of these players who had just finished the match. He had played 30,000 hands personally against this AI, and
Say that again. How many?
30,000 hands of poker
Against
Liberatus, yeah. So overall, the four players played 120,000 hands, so we could get statistical significance and to give the humans the best chance to find holes in the AI. So you want to play a lot of hands.
How long would that take?
20 days. So 80 days total of work done in 20 days.
Yeah.
So she was asked, can you come up with an example where the AI exhibited this type of behavior? and he would recall that hand out of the 30,000, just like that.
That's amazing. So I mean, I'm amazed at what human intellect can do. As we're sitting here, being immersed, situated in the situation, understanding each other's language abilities. But when you take a constrained game with such complexity like that, and the human beings become specialists. They just do great at this. They have memory. They have indexes into what happened.
Yeah.
Strategy. It really is impressive.
Very impressive. On the other hand, they do nothing but this all day long. so they do become specialists.
Well, so speaking of that topic, what about, and I'm sure the goal was not necessarily just to beat the best players at poker. It was about to understand machine intelligence better. So what have you learned about AI and the process of working with Libratus and where it went, per generalizable principles, and other kinds of problems you might solve in the world, in the open world?
Yeah, so that's a great question. So one is that these techniques are not techniques for poker, therefore imperfect information games in general. And as I think about it, most real-world situations are imperfect information games, even if they're not treated as games today.
Give me an example, make it clear.
Pricing. So typically companies, when they optimize pricing, they treat it as an optimization problem, assuming the competitors' prices are fixed. And then when the competitors change prices, then you re-optimize. You're always kind of in a reactive mode behind the 8-ball, while if you think about these pricing moves ahead, you can actually do what I call strategic pricing. And this kind of thing happens in a lot of industries: finance, investment banking, sports, video games, and so on. So this has a lot of applications, and I'm actually so excited that I've founded 2 companies to field this. One is called Strategic Machine, and then for government applications, Strategy Robot. We're taking these techniques that we've developed in the lab over 16 years now, fielding them into a bunch of things. So one is that I think you do need to think about imperfect information. You do need to deal with opponents trying to deceive you, and so on. So that's one. The other is there's a lot of talk about oversight of AI. And we got into this point, and I don't think it's just us, I think as a community as well, where whenever human players, top players even, would say that, no, that's a mistake, I would actually know that chances are that the human is wrong, not the AI. So, the human oversight question really became...
Which application are you talking about?
Poker. I'm talking about poker. Yeah. So there, even the best poker players, when they would say that, okay, that was a mistake...
You mean a poor move?
Poor move.
Yeah.
Or a poor strategy. Sometimes you can't think about the moves in isolation. You have to think about whole stretches of moves.
Even with the AlphaGo story, we saw examples. That's a poor move, and it turned out to be a unique and interesting new kind of move.
Sometimes these superhuman moves or strategies are not really easily evaluable by humans. So when humans say that's a mistake, maybe not. And I think that's something that as we want to get humans to be augmented by AI, we need to think about how do we deal with the fact that humans can't really provide proper oversight for AI. And AI may also have its own weaknesses in providing oversight to humans. So there should be this kind of mutual oversight. But how do you do that really when humans can't evaluate superhuman moves?
Okay, so where are you're thinking on directions there? Feel free to speculate in real time.
Okay.
If you haven't solved the problems yet.
Okay. Well, I actually don't really think that humans can provide very good oversight for AI in the long run because they don't understand superhuman moves. And so that's one. And other is that for a while, as you get superhuman moves, you can give humans extra data around that decision and give them time to understand them and evaluate them and try to understand why wasn't it good, why was it bad, and so on. And we actually did this. Chris Ferguson was looking at our moves sometimes offline where something looked like a really bad move to me or to one of the top poker players, and we would actually isolate it and we would show, okay, at that point, here were the belief distributions of the AI, here's the belief distributions that the AI would have had if it were in the human's shoes, And from these belief distributions, was that a good play? And with 3 days of analysis and oftentimes a little essay to go with it, Chris was able to say that actually that looked like a dumb move, but it actually is like thinking 2 levels deeper than humans ever do, and it's actually a brilliant move. So with some hindsight and time and extra context, humans actually are able to appreciate and evaluate superhuman moves. But I think that'll go away. That'll only go for a while when the superhuman moves aren't too superhuman yet. But once you get beyond a certain point, I don't think so.
And in the open world, we have to assume that some moves advertised as superhuman might be erroneous, might be actually wrong.
That's right.
And so if people get used to accepting moves they don't understand, the opacity there, it's unclear what the policy should be about humans actually providing some oversight and being able to stop things or shunt them or modify them.
Yeah, and there's also, if you think about things like robots, where you have to do it in real time, do you take over the controls or don't you? And the AI might have driven you into a situation where it can still recover, but the human can't, because the human doesn't go into those state space parts and so on. So it's a very complicated question.
Unless we have validation and some notion of trust, it might turn out that we have to give robotic systems, automated systems, the ability to downmode so they're doing things that are understandable to human beings, so they can be understood and guided if necessary.
Yeah.
Which might be a gentle trade between total optimality and winning a game, for example, and just doing a great job.
Yeah,
it's understandable.
I do think, in some applications it might be a gentle trade, like, hey, are you going to take over the wheel on the car? Yeah, that's probably a gentle trade. So, but in other applications, I think the trade-off won't be that gentle. And we may have to give up in some applications the human understandability.
Well, certainly you might not win a poker game if you gave up the best moves.
Yeah.
Interesting. So tell me a little bit about Strategy Robot and why this interest in helping governments with their projects.
Well, it's actually, I started it with the strategic machine first, which was really for everything. And then it turned out that the potential customer bases are totally different and other requirements are different, so I actually had to split it into one for the commercial side, strategic machine, and then one for the government things, which is strategy robot.
Tell me more about the government work. What kinds of problems are you solving there?
So far, we're targeting things like military planning, cybersecurity applications, intelligence, wargaming, training, things like that.
Very interesting. This whole area of AI you've been in for many years, and it's fabulous. We're both involved in this wonderful long-term mission to understand intelligence. There are different perspectives, different approaches, different methodologies, but certainly a big difference in point of perspective is people who work on kind of central algorithms and deeply coordinated approaches, and kind of the people that often rely on the power of distribution methods, theorems, equilibria, seeking intelligence in a system as the sum of many, many parts that are interacting with certain properties. I'm curious where you are these days and you're thinking about you at the foundations of human intelligence, the importance of central coordination versus distributed processing.
Okay, that's a big question.
I don't ask little questions. Well, I guess I did a few minutes ago, but this is a big one, yeah.
Okay, so I started out by thinking that, part of the reason for distribution is autonomy, and part of it is computational efficiency. And those are kind of, the distribution is the same for the two. And in the Draconet system, that's an example where we did distributed negotiation peer-to-peer, totally distributed. But then when I moved to combinatorial auctions around 97, it became clear that you can actually get better allocations and more efficiently by having a centralized clearing point, like an auction server, combinatorial auction server with centralized optimization algorithms doing the allocation. So then there was this autonomy notion of different bidders, but it wasn't from a computational perspective. And from a computational perspective, it was actually better to centralize. And now, if you think about how the that works. For example, we built our own hosting service. We were a software as a service company, one of the first analytics software as a service companies. But today it would be cloud and is at Optimized Markets, which is a combinatorial market company that I'm running. There, the distribution, kind of the autonomy-based distribution, self-interest-based distribution is totally different than the computational distribution, in that from the player's perspective, it's a centralized marketplace, while from a computational perspective, the clearing engine or the marketplace driving optimization, that is distributed in the cloud across multiple servers, but those are all in the centralized clearing point. So the distribution for autonomy and the distribution for computational speed, they're totally different. They're both in the same market at the same time, but they're different.
So there's no summary answer, or do you think we have to have just intellect on both kinds of processes? Coordination might always be necessary at some level, more centralized?
I wouldn't say it's always necessary, but especially when it comes to these combinatorial problems, getting good solutions, or let's say optimal solutions, or near optimal solutions in these combinatorial allocation problems, it is very hard to do in a peer-to-peer way without a centralized clearing point. So maybe it's just my experience, trucking being the least sexy but most combinatorial problem ever. You know, that's maybe kind of driving my thinking of that. But we saw that the more combinatorics there are, the more benefit there is to a centralized clearing point.
Given all your experience, Tuomas, I don't usually ask this question to folks, but I thought I'd get you to speculate in real time. What do you think's going on in the human mind? What's your favorite? Well, give me your intuitions about what might be going on that performs all this magic.
I kind of made a commitment fairly early on not to worry about it too much.
I didn't say worry. I said, what's your best you must have some guesses and some inspiration, some thoughts, insights, even if we know they're just guesses right now. Because sometimes these guesses guide our research, and even though we don't talk about this very much.
I mean, maybe less so. I actually, when I was picking a research topic in the 80s, one of the other areas I was very interested in and had done some things was deep learning. And I guess...
you mean like connectionism in those days, as we called it?
Yeah, neural networks.
Yes.
And I was very interested in that. And just kind of by half fate, you know, this is more, the game theoretic strand is more kind of where I went. And for better or worse, it's been an interesting ride. But I kind of don't know so much about what's going in the human mind.
But it sounds like that was an early curiosity of yours.
Yes, very much.
Maybe even have powered up the whole AI direction.
Yes, very much.
So we'll keep it at that right now, and
Okay.
we won't speculate, especially on video.
Okay.
Turning to other people, you've been a great mentor to many students over the years, and you've had a very successful career and much more to come. What are some words of wisdom you'd like to share with young folks about career more generally, even inside or outside of computer science?
Okay, interesting.
Now, you probably will never in video or anywhere else be asked those two different questions side by side. How the brain works and what your thoughts are there.
So yes, in computer science, my advice would be that make sure you have some real-world problem that you work on, because it will fuel a lot of interesting research questions into the research agenda. And it's very hard to come up with those questions that are significant if you're just sitting in your office with your feet on the table trying to flip through proceedings. So it's better to be the person who publishes a first article on some topic and brings a new question into the field, rather than being the guy who flips through the proceedings looking for potential improvements. That's my opinion. We've done some of the latter too, but I think that's been less impactful. Then interdisciplinary. So I found that it's been great to be able to draw knowledge from multiple different fields. So one example is the game theory and optimization intersection. Another is really the intersection between AI techniques and integer programming techniques. These fields didn't really talk to each other much, and this was tremendously helpful. And now they talk to each other much more, but it was really great to actually know the techniques from both sides and being able to contribute to that intersection. with both types of tool sets in hand. And so just reading on both sides, reading broadly, and not drawing boundaries. Instead of thinking about, hey, in a paper I sometimes see people write, computer scientists think this, economists think that, or things like that. I would never mention a field of science in a paper. And I encourage that nobody else does either, because that erects boundaries between fields
Right.
instead of taking them down. It doesn't really matter whether it was an economist or a computer scientist or an OR person who said this or that. That's really irrelevant and a waste of space in a paper.
Fabulous. Well, with that, thanks very much. It's been great talking
Thank
to you.
you.